So as part of my continuing series on how I'm building my CNC machine, which I'm calling Axis, I shall be covering some of the information that I feel is useful to know that I've discovered on my own and don't think is very common, or anything really that I think may be useful to know if you're building a CNC or a 3D printer on occasion. So in this episode, I am going to be tackling linear actuators, which are basically any system that turns the rotational motion of a motor such as your stepper motor for your printer or CNC into the linear motion that you need to move along an axis, so your X, Y, or Z. So without any further ado, I shall launch into my first category. Now here we have a threaded rod, also known as studding or studded rod. These are available at pretty much any of your local hardware stores. They're basically designed for workmen and engineers to quickly and cheerfully bolt things together in some form or other. Now the pros of that are that they are extremely cheap. A meter of this would cost around £2 to £4 perhaps, which is really good going when you think about it. The con of it, however, is that the tolerancing is usually really bad. So on the pitch, which is basically the number of turns that the thread makes per unit length, so here in the UK that'd be per millimeter on the metric system, that can vary a bit depending on the quality of obviously the studded rod, which, because they're turned out cheaply, tends to be quite low. So that means that sometimes your nut will catch, or it will go a slightly smaller distance than usual, or slightly greater distance than usual, which means that you've basically got a slightly different layer height, which, you know, it can be ignored at the small micrometer scale, but in general you want to avoid that. So that's the pros and cons of these things. Next up, we have a lead screw. Now this, unlike our previous studding, is designed for your linear motion. As such, it has much better tolerances and tends to have a much larger pitch, so that each turn is a larger distance, or takes the nut a large distance. So if I was to rotate this for one turn, that would be your pitch. It's not very obvious on the camera, but get yourself a piece of either of these and test it out and you'll see what I mean. Now these tend to be, because of their high precision and smooth finish, they tend to be more expensive. This is a 400mm long one, and I got it decently cheaply actually at £15. Now that is 3 or 4 times the price of that, but in my opinion the quality is much better and you get much better value, so long as they don't bend in the post, which occasionally happens and is one of the things that you need to watch out for when you buy these things online. If you buy any of these online, do try first to search for a known brand or one that you know will ship it properly. Those tend to be more expensive, sadly. But the worst thing you can have is for one of these to arrive in the post and then you realise that it's not straight and this will actually veer slightly as you're printing. Now the easiest way to check that is to remove any paraphernalia or excess materials from this and then roll it across a surface. Now assuming that this is a completely flat surface, it's not, you would be able to see and hear and even feel any variations in how it's bent, because a bent object, when it's rolling, will obviously move around. So if it's perfectly straight, you should get a very nice roll. Now thankfully, this is. So with those aside, there are 2 others which I don't have to demonstrate here, but I would like to go into them anyway, because if you have the money to spare, there are definitely things to consider. The first is what we call a ball screw, which is basically a lead screw, but even more efficient. A lead screw is around 40 to 80% efficient, if I remember correctly, depending on a whole lot of variables. Ball screws tend to be around 80 to 90%, if not more. And the reason for this is that instead of this helical cut that you see here, they have round cuts in it, and the nut that runs along it actually has small ball bearings that move through. And that just gives you a much better motion with much higher tolerances and a lot less friction. Now I can't quote a price because I haven't looked at these before, but you're talking a whole lot more than with these. Now the final type, which I definitely probably will never actually use, but I just came across them recently, a really fun little type. If I can quickly grab a pen here. Say you have your studding there, or sorry, your thread of any kind there. What they're basically doing is they're then putting a second thread, like so, and then they put that with a toothed gear here, so imagine that's a tooth, and then a large planetary annulus that runs along that nut, and basically it's pretty hard to envision unless you know what I'm talking about, and looking at some 3D images online will probably be very helpful. But what basically happens is that as that rotates, it moves through the teeth and the entire system moves, or you can rotate the annulus and actually drive these screws along. It's basically like the worm gear equivalent of a planetary gearbox. Those tend to be very expensive, but I hear they're even better than ball screws. Now, when using these on your system, if you're using them for your 3D printer, then chances are you'll just be using them for Z, so you don't need to worry about backlash. Now backlash is this. As you can see, holding the shaft completely still, I can move the nut ever so slightly up and down on there. Now with these, you will find these lead screws, proper lead screws, and in fact ball screws and other such systems. If I can find a good end to put this on, there we go. You'll find that there is a lot less backlash. You can see a slight bit of movement. However, if you're using these on your 3D printer, you don't need to worry about that, because gravity will be fighting against that, and there's no real force to push it up to any noticeable degree. So yeah, that's not an issue. However, with your CNC, there are a lot of different forces involved, and you will be tending to use these for your X and Y as well as your Z if you do choose to. Now the issue there is that there's not really any force to counter your backlash, especially if your drill bit is cutting through in the different directions. It will tend to shift ever so slightly. So the easiest way to get rid of that with these systems, I will demonstrate here because I don't have another nut on this, but the easiest way to get rid of your backlash is to have a spring in the middle, hold that in whatever your mounting system is, and tighten up there, then hold it at pretty much the same angle that you would here, but make sure that you've got it tightened a decent amount. Now what you'll notice is that both of these don't move as much. You can see here I'm having to apply a decent amount of force to move that at all. And the general principle here is that they're being pushed out against the teeth. In fact, let us draw another quick diagram. If you have your teeth here like this, I'm just going to draw 3 for the sake of it. That's your tooth on your shaft. This is a tooth on your nut. And what's basically happening is there's a slight distance here that's not being accounted for, so obviously it shifts slightly in those directions. Now if you apply a force from a spring here and here, you basically push that surface there and that surface there, which eliminates your backlash. Now keep that in mind if you're using it on a CNC. If you're using it on a 3D printer Z-axis, don't worry, it's not going to affect you. Yeah, it's just not going to affect you. If you are using it on your X and Y though, however, do worry, there is something to be considered there. Now the other thing to note with these is that they're a very different pitch. Now, like I mentioned before, pitch is basically the number of times that the thread circles per unit length. Now, in your CNC, you're going to be moving a lot faster than you would be on a 3D printer, that only being the Z-axis. So with this smaller pitch and the poorer tolerances, you really shouldn't be using a bit of studding unless you're going for a very cheap and cheerful machine. So at the very least, I suggest getting a lead screw. They can be quite expensive and price will build up, especially if you want to get one that's perfectly straight. However, you know, that's one of the sacrifices you have to make. Now, continuing on to our second category, we have the belts. In this box here, I have a nice little collection of belts and pulleys. Now, this is a GT2 belt, by the way, which is actually a bit of a misnomer. It's actually a 2GT, but, you know, this kind of stuff happens, which basically means it's got a pitch of 2, and like I said before, the pitch is basically how many teeth or what distance you are traveling per unit length. So this has a pitch of 2 millimeters, which means that every tooth is in effect 2 millimeters from point to point. Now this is a closed loop here, but basically what happens is that with your pulleys in the groove there, you can transfer your motion along an axis. Now this you'll see very commonly on a 3D printer on its X and Y axis. You'll see it much less commonly on a CNC machine, or at least a professional one. Some of the cheaper models you might, because the belts need to be quite strong to take the loads. These are actually pretty decent, but they will stretch over time. You can get them in bigger sizes. I think this is a T5 belt. I'm not sure, I got the second hand. But yeah, belting is one option you have for doing your linear motion systems. Now, on top of that, I'm going to be adding in 1 or 2 other versions. My preferred version for just now, the chain. Now, the chain is like the belt, quite versatile. Instead of stretching as the belt can do, it doesn't, but it can instead sag because it has a lot of weight. Now that can be combated in a number of ways, including pulling it very, very taut. The other issue with these though, however, is that they are, well, they're not very accurate compared to some of the other systems. The nearest comparison is to the threaded rod, where this is designed for engineers and builders to just quickly put things together. This is a bike chain, and bike chains are designed to transmit power and not accuracy or precision. You need to be very careful with these. You need to design an anti-backlash system, in my opinion, to make sure you're getting the most out of them. And this is actually what I'm using for my CNC because they are nice and cheap, and I'm trying to make my machine as cheap as possible. So what I've designed here is a very simple anti-backlash system. I have here 2 sprockets, which go between the teeth, much like the gears here will do. The pulley, sorry, will do. And what I've got in the middle here is a spring. Now, springs are your friends for removing anti-backlash, like we had the compression spring here. We now have a torsional spring here, and basically what that means is that this can flick back. So if you tighten that up and press it into place between the teeth here, it's basically going to push one of these one way and the other one the other way. Now if these are held completely in line, then that basically means that the wobble, as shown here, has been removed. So that's the system that I'm going to be using. You're free to choose your own system, obviously, but I think given the price of these, £6 for $1.70 m, if I remember correctly, that's probably the best system to use. Now, one other option that I have not really seen much is to use wire. Now, instead of using the teeth, what you would do is you would use a round pulley like that, preferably one with a higher coefficient of friction, and by twisting the wire around a few times, you've basically increased your surface area, and you want to do this more neatly when you actually use it. But by turning that, you can pull the wire one way or another. Now, I don't like this as much because I feel the mechanical advantage of teeth is that you do have something physical to stop slip. With a pulley and wire, you're basically relying on the coefficient of friction to be your friend here and save you from slipping. With these, if you do manage to skip a tooth, you can hear it, or you can see it more easily because it's a more obvious move. With these, they can slip gradually over time and you probably wouldn't notice. So that's why I wouldn't suggest using a wire, but for very, very cheap machines, you probably can. Actually, they're decently cheap. I think this was about £2 for about 2 meters. So yeah, go for that if you want. Now the third option the third category, if you will, that I haven't covered yet, are the rack and pinion. Now a rack and pinion simply means that you have a gear, excuse the extremely badly drawn gear, those are teeth, that's the middle, in case you were confused by that terrible drawing. A rack and pinion basically uses teeth like that, and by rotating this, you move along that way. Those are quite nice, but they tend to be very expensive as well. A length of about 300 millimeters of pinion that I found, plastic, let alone metal, cost about £30. It's ridiculous. Unless you have the money to spend, I suggest not doing it. You can print them, I suppose. You can print them and use a similar system to here to remove backlash. But, you know, I feel that the chains might be cheaper and easier in the long run. To go back and talk a bit about the different ways that you can drive your belts. Now, assume, for sake of argument, that this is a cut belt and not a closed loop. Most traditional machines, you'll see, have the motor at one end, an idler at the other end, an idler being a gear or pulley that just turns without any input force, and it's just there to, you know, help transmit the motion and load. And they will pull the belt taut, and then on the middle you will have clamped your system. This is very commonly seen in the Prusa. That's a very good example. And as you turn the motor, it pulls the other system along. So on your x-axis, you would pull the y-axis along if you were using a H-bot. There are some other methods, however, that I think are fun to explore, and for this I will use an open belt system, such as my chain here. The other option is to have it open, clamp each end to basically your bed surface or your rigid frame, and the advantage here is that for the amount you're paying, you're getting twice the length, really. Imagine if this was a closed belt. In fact, let's draw this again. If this was a closed belt like that, then the length you're getting here is roughly, allowing for, you know, the curves and everything, roughly half the length of the circumference of the belt. If you were to then cut that and lay it out flat, you're getting twice the distance. So if you were to clamp the ends really nice and tightly, the option that I'm going with is to use my pinion, like so, and to run along them as if it was a rack and pinion. The other option that I've seen, and that works quite nicely, judging by its popularity, is what they call the Omega Drive. And in this system, you would have your pinion here, but you would also have some idlers down here and here, and the tension of that can be adjusted. And the basic idea is that, in the same way as with the rack and pinion, as it moves, it'll just pull itself along. So yeah, those are the different options you have for assembling that. There are probably quite a few others that I haven't seen yet or haven't come across, but those are just the basics for now, and the video is getting quite long, so I'll end it there. On my next video, I'm going to be talking about the linear tracks and rails which we use to run along, for example, V-slot and other such. Now, if you are using V-slot, stay tuned for that, because I'm going to be exploring two of the methods that I have experimented with and that may be of use to you that are cheaper than V-slot wheels. So with that said, please do come again next week. Please let me know what you think of all this, and yeah, any comments you have, any feedback, very much welcome. If you have any others to suggest, please leave them down in the comment section, and I look forward to talking to you again later. Goodbye.